Good to go. All right. Thanks everyone for coming. Welcome to our sixth Compass lecture of the fall 2023 semester. Today, Shimon Kolkowitz will be talking about testing relativity in the lab with ultra-precise atomic clocks. I think a lot of you already know Shimon maybe, but just to give a bio. Shimon Kolkowitz is an atomic physicist and quantum scientist with experimental research focusing on quantum sensing, precision measurement, and metrology. Shimon was an undergraduate at Stanford University, graduating with distinction in 2008 with a BS in physics. Shimon earned his PhD in experimental physics at Harvard in 2015 with advisor Professor Mikhail Lukin, where his research focused on quantum sensing with defects in diamond. He was subsequently a National Research Council postdoc fellow at NIST in Boulder in the research group of Professor Jun Ye from 2015 to 2017, working on metrology and quantum science with optical lattice atomic clocks. Shimon held a faculty position in the Department of Physics at the University of Wisconsin-Madison from 2018 to 2023. And in 2023, Shimon joined faculty at UC Berkeley, where he is currently an associate professor of physics and holder of the Herst Chair. He is a 2019 Packard Science and Engineering Fellow and a 2022 Sloan Research Fellow and a recipient of the NSF CAREER Award. So without further ado, let's welcome our speaker.
Okay, thanks a lot for the very kind introduction. I think I wrote probably, but thank you for the invitation. It's great to be here. Thanks everybody for coming. The first thing I'll say before I start is that I do want to keep it super informal, and so please just ask questions throughout the talk, and especially I tried to keep it approachable. And so, but if anything I'm talking about is kind of unclear, you know, just please speak up and I'll try to explain it better. And that goes for people on Zoom as well. So I want to tell you a little bit about the work that we're doing in my group on testing relativity in the lab with ultra-precise atomic clocks. One thing Vikram mentioned that I just moved from Wisconsin, and in fact my group is still there. So these experiments were actually done in my labs at Wisconsin, and the experiments are actually still running back in Wisconsin right now. But the plan is for them to move here to UC Berkeley in this late spring or early summer, and they'll continue here. Okay, so here's the outline for the talk. I'm going to start by giving an introduction to clocks. I'll tell you, what a clock is and what it can be used for, and specifically atomic clocks. And then I'll tell you about a specific kind of atomic clock called an optical lattice clock. These are currently the best clocks that humankind has ever made. And I'll tell you about a new kind of optical lattice atomic clock that we built in my group, and then how we're using it to test relativity in the lab. So first of all, clocks talks about clocks. So, it might seem like a silly question, but what is a clock, right? And of course, I think when we think about clocks, we probably think about the one that's just right outside. I'm not very well oriented, so I don't know which direction it is, but somewhere outside of this building, right? That's the Campanile. But, this is just the thing that's telling us what time it is according to the clock. The real question is, how is that thing actually keeping time? And the way any clock works, including the very first kind of modern clock, which was the Huygens pendulum clock, and sort of invented by Christian Huygens, building on work by Galileo on sort of explaining how simple harmonic oscillators work, but is just based off of counting the oscillations of a pendulum. But this is how any clock works. Basically, any clock works by counting something that has a periodic sort of rate or frequency associated with it, and you count the periods of that oscillatory phenomena and use that to keep track of the passage of time. And so the nice thing about a pendulum is that it's a form of simple harmonic oscillator, and so the frequency that it, to lowest order at least, the frequency that it swings at doesn't depend on, for example, the amplitude of the motion. And also another nice feature about it is it actually doesn't depend on the mass of the pendulum. So if a piece of dust or something settles on your pendulum, it continues to tick at the same rate. Okay, and so so you can just write down, what the frequency of this thing is. Of course, it's not so convenient to sit there and count every single oscillation of a pendulum. And so the other piece of a clock that you need is something called an escapement or a counter. This is a mechanical counter that can convert the ticking or the swinging of the pendulum into the ticking of the hands on the second hand, sort of showing you here on the front face of your watch. And that does the counting for you so that you don't have to sit there and count every single oscillation. Okay, and so that's actually all that you need for a clock is something like a pendulum or a hairspring in a watch or something like that. But then there you can ask a natural question, which is how good is a clock, or how do I parameterize, how good is a clock? And this is also a very intuitive thing. You can imagine building two campaniles and having them next to each other, and then saying, well, do they agree on the time, right? And if I start them, if I set them both at some time let's say when I build the two towers and the two clocks and I start the pendulum swinging and I start them saying, it's noon on us, on some date or something, then sometime later you can come back and say, do they still agree, right? And basically the thing about clocks is no matter how good the clock is, at some level, there's going to be some imprecision in keeping track of time because these are man-made things. They have man-made oscillation, the pendulum that you're using to keep track of the time or whatever the thing is. I'll give you more modern examples in a minute. There's going to be imperfections in that, and there's also going to be imperfections in my ability to measure it. And both of those things will cause these two clocks to drift apart from each other over time. And so we can actually parameterize how good a clock is. You can look at Huygens pendulum clocks as an example. What actually limited the accuracy of these clocks was that the length will change when the temperature changes. As you probably all know, if the temperature in the room changes, things have a coefficient of thermal expansion. And so they'll expand or contract as the temperature, drifts around. And that causes the length to change, and that causes the period to change. And so a lot of the early research into clocks was actually devoted to just trying to find alloys that had very low coefficients of thermal expansion near room temperature so that these clocks would be more stable. The Huygens pendulum clocks were accurate to 15 seconds per day, okay? And this is actually the number that we're going to use throughout this entire talk to characterize how good a clock is this fractional, this fractional number, which also is related to what's called fractional frequency uncertainty. But basically it says, it's one way to understand how many seconds does it take to lose a second, okay? So you take, and then you take the inverse of that. And so, for example, there's about 10 to the 5 seconds in a day. So if it loses 15 seconds in a day relative to another clock, then it's 2 parts in 10 to the 4, or 2 times 10 to the minus 4 is the parameter that we care about. Okay, of course, this is not what most modern clocks, and actually I was trying to figure out what's in the campanile, and I don't know. If anybody knows, I'd be curious to know. But modern clocks are a little bit more sophisticated. So inside of all of your cell phones, or inside of your laptops, inside of your watches, most at least digital watches will have one of these little quartz tuning forks. This is just a version of a simple harmonic oscillator. What's nice about this is there's 2 features that are really nice about it compared to the pendulum clock. One is that this thing is piezoelectric. So you can measure the frequency electronically as opposed to mechanically. You no longer need a mechanical escapement. You can now use a electronic counter to keep track of the oscillations of this tuning fork. And the other nice feature is that it actually oscillates at a much higher frequency. And that allows us to make a better clock. And this is also kind of an intuitive thing, because if you imagine trying to keep track of the passage of time, if your clock only ticks once per second, if it gets a little bit off, that leads to a much larger error. Whereas if it ticks 1,000 times a second and it's a little bit off, that will be a much smaller kind of fractional error, right? Or another way to think about it, if you want, is that it's much easier to figure out, exactly, when a second has passed when my clock ticks 1,000 times a second versus when it only ticks one time a second, right? And so either way, you can understand that actually all other things being equal, the faster your clock ticks, the better the clock is. And these things, like that's in your watch or in your laptop, or especially you might notice it on like an alarm clock or a microwave, something that doesn't talk to the internet. Those are still man-made objects. They still drift around with respect to each other. You can see a nice plot here in this fractional frequency unit, delta F over F. And you can see that it's drifting in the kind of part per million level over the course of days, and in about a month, or so these can get off by, a fair bit. And so so you might notice that like your microwave or something starts to disagree with your phone, on the minute scale in a matter of months or something like that. It'll start to get fast or slow by a minute, something like that. Actually, what gives you this nice kind of continuous curve is the aging of the quartz of the tuning fork. Anyway, so you can actually do some things to account for that, but then even on top of that, there's additional noise and everything. Okay, and so this is again the kind of this tells us how good one of these things will typically be, and so it's about precise to something like 3 seconds in a month or something, or roughly speaking, and then over the course of a few months, it'll get off by minutes and things like that. So that's fine for deciding when to meet or when to come to a lecture or something like that. That's more than good enough. But for physics, for measuring things in physics, we actually need to do better than this. And we'd all like to agree on frequencies and on time when we're making measurements of things. Actually, being able to measure time and frequency is really fundamental to doing almost any physics experiment. And so for that, we need an atomic clock. And the idea here is actually an atomic clock is the same as all the clocks that I already told you about. It still has one of these little quartz oscillators or local oscillators. It still has a counter. The only difference is that you now introduce something called a frequency reference that you're going to use to correct for the drifts and imperfections in these man-made local oscillators. Okay, and the idea is that from quantum mechanics, we know that atoms have internal atomic transitions. There's this kind of quantum weirdness, this weird effect of quantum mechanics that's somewhat counterintuitive, that the electrons around orbiting around a nucleus can only have certain energy levels and not other energy levels. And these are very well defined. And so we can take advantage of these of this, combined with the fact that light can induce transitions from one energy level to another, and that therefore you have very well defined frequency of the light that gets absorbed or emitted when an atom makes a transition from one level to another atom. One level to another, we can use this. So here, for example, this is showing you, if you look at a neon, like a discharge, a plasma discharge neon lamp, and you look at all the spectra, all of these correspond to different transitions of the electrons of the neon atom, changing from one state to another, and you get these very specific lines at specific wavelengths or colors, which corresponds to specific frequencies. And we can use that to then check what the frequency of our local oscillator is. So the kind of experiment we do is we prepare an atom in a specific state, and then we shine microwaves on that atom, and we see, did that atom get excited from one state to another state? And we know how to measure that. We know how to count whether the atoms have gotten excited or not. And if they did, we know we're on resonance with that transition. But if if our local oscillator has drifted off of resonance and we do the experiment again, now it didn't get excited, right? And so just by counting how many atoms got excited and keeping track of that, we can actually sit on the edge of this transition and feed back to correct for the drifts of our local oscillator and the imperfections of our local oscillator. And because every cesium atom or every rubidium atom is the same as every other cesium atom or every other rubidium atom, now you can make one of these atomic clocks and I can make one of these atomic clocks. And to the extent that we can do this comparison between the local oscillator and the atoms, our clocks will be the same, right? And so now the only thing that kind of limits the performance of our clocks is no longer the man-made nature of this or the fact that that the material ages or the temperature changes or anything like that. What now determines the performance of my clock is how well can I do this comparison between the frequency of this radiation and the atoms. And that turns out to be limited fundamentally by just a couple of things. One thing that it's limited by is how wide is this transition? Because the narrower the transition, the easier it is, the more precisely I can tell whether exactly I'm on resonance or not, right? And the more sensitive I become to small changes in frequency. So that's one thing. Another thing is how many atoms do I have? Because actually from quantum mechanics, as I told you, the atoms can actually only be in certain states. And so when I measure each atom, I project it into either being in the ground state or the excited state. And I just count how many atoms were in the ground state or the excited state. And so if I'm sitting on the edge of this transition like this, I'm actually just doing a bunch of quantum coin flips. Okay, I measure each of these atoms, and there's a certain noise associated with that process because it's random, if I'm really sitting right on the edge and there's a 50% chance of it being in the excited state and 50% chance of it being in the ground state, it's really like flipping coins. And so you can write down from that, what process was called quantum projection noise, you can write down this equation. It's actually a very simple equation that only depends on a few things to say how good this atomic clock will be, okay? And basically, most of atomic clock research has to do with trying to kind of use this formula, this equation, to kind of improve the performance of the clocks over time, okay? And since the kind of invention of the atomic clocks in the first demonstrations, clocks have gotten very, very good. So the first clocks were demonstrated around 1950 or so, the first atomic clocks. And since then, they've been improving a factor of 10 every 9 years or so until the early 2000s, to the point where these microwave clocks, which are based off of cesium or rubidium, are now accurate to 1 second in 300 million years, which is a really impressive number, right? So what that means is you have two of these clocks ticking side by side for 300 million years, and they would still agree exactly on the time or on how long they've been ticking for to within 1 second over 300 million years, which is pretty amazing. And that gives you access to all kinds of new things and new applications of these clocks. So in particular, one thing that I think we really take for granted, but really would not work without these clocks, is the GPS network. So you may or may not realize this, but the way the GPS network actually works, the way your phone knows where you are, is it's just it's getting signals constantly from a bunch of satellites that are orbiting the Earth. And each of those satellites has an atomic clock on board. And those atomic clocks, all they're doing is broadcasting constantly what time it is and where they are, okay? And then because there's a finite speed of light, the arrival time of those signals is different depending on which satellite you're talking about and where you are on the Earth. And so you can your phone just triangulates that signal. It just says, okay, this satellite, I know where it is and I know what time it is telling me. And then this other satellite, I'm getting a different time and this one's a different time. So based off of that, you can triangulate and figure out exactly where you are on the surface of the Earth. And this only works because we have clocks that are precise enough relative to the speed of light, which is very fast, and the distance to these satellites from the surface of the Earth, which is not that big. Okay, so this requires very, very good clocks, and this would not work without atomic clock. Another example of kind of how important clocks have become to physics specifically is in unit definitions. So we've now gotten so good at making clocks that actually we can make better clocks than we can make any other kind of measurement device that measures things with units. And so recently we actually switched to a new system of units. This is called the new SI, where every single sort of unit, aside from the mole, which is just a number, okay, every single unit is actually just related to sort of other units, which are all related to just fundamental constants that we define. So all these things in gray are numbers that we write down, and you can't measure them. And the hyperfine transition of cesium, which is something that we measure with an atomic clock. So literally, your extent to measure anything with units is determined by how good of a clock that you can make, ultimately. It all gets traced back to your definition of time, and your definition of time is traced back to atomic clocks. And so at this point, if you want to measure anything with units, your ability to do that will fundamentally, ultimately, in the end, of course, there can be other things that limit you before that, but will ultimately be limited by how good of a clock you can make. Okay, and so that sort of motivates making better clocks. One other thing I'll say is there's actually other things you may or may not realize use clocks in kind of subtle ways to, for example, it make topographic maps of the Earth, or to communicate securely in combat zones and things. There's actually a lot of other applications of clocks that are that are pretty subtle, and they get used in other kinds of navigation devices and things like that too. But okay, but so just from a physics perspective, we need better clocks because it determines how well we can measure anything. And so that motivates kind of trying to make better clocks into developing even new kinds of clocks. And so if you look at this equation, okay, you can see that there's a few different things you can do to make a better clock. You can add more atoms to it. You can try to measure the atoms for longer, which means you have to hold them or trap them in some way, which I'll talk about more in a little bit. You can try to find a transition that's narrower, but we're kind of stuck with the transitions that we have. But the last thing that makes a big difference here is this parameter of nu naught, meaning the frequency of the transition that you're using to make the clock, okay? And all the clocks I told you about and showed you so far, all the atomic clocks were based off of hyperfine transitions in hydrogen-like atoms, hydrogen, rubidium, cesium. These are all microwave transitions. They all have frequencies of tens of 1 gigahertz to 10 gigahertz or so, okay? But of course, you probably know, and I showed on the previous slide, there's also optical transitions in atoms, which can have frequencies at 10 to the 15 hertz at hundreds of terahertz frequencies, right? And so if you can make a clock that uses, instead of these microwave hyperfine transitions, uses optical transitions, you in principle can make a clock that can be sort of 10 to the 5 times better. Okay, and the way to understand that is it's just the same argument I already gave you. Basically, this is a clock that ticks faster. And so it's like adding, finer degradations on your ruler and making a more accurate ruler, okay, and a more precise ruler. But to do that requires some additional stuff I'm not really going to talk about. You need some way to actually count the frequency of light. That's a very non-obvious and not easy thing to do. Light, optical light, oscillates at a frequency that's much faster than our electronics work at. And so you can't make an electronic counter the way you can for a microwave transition. However, there's an invention which was part of the 2005 Nobel Prize, is something called the laser frequency comb or the optical frequency comb. And this is basically a thing that allows you to actually count the oscillations of light and the oscillations of a laser. And this allows you to make an optical clock. Okay, so that's one important new ingredient that we have just in the last 20 years or so. Another thing that you need to do is you need atoms that have optical transitions that are still very narrow, okay? And it turns out that the atoms that we were using, which are quite simple and easy to work with, which are in the first column of the periodic table here, these are hydrogen-like atoms. They have very narrow hyperfine transitions or microwave transitions, but they don't have narrow optical transitions in general. And so you actually need to move over one column on the periodic table to work with slightly more complicated atoms like strontium, or it turns out, it's not obvious, but ytterbium is actually an alkaline earth-like atom. So it actually kind of has the same level structure as the atoms in this column. And so these are two atoms that we use to make very good optical clocks, okay? And so if you look at the level structure of these atoms, they're more complicated than these hydrogen-like atoms because they have 2 valence electrons, okay? And that more complicated level structure gives rise to these very narrow optical transitions that we can use to make a clock. And in particular, this transition here, I'm not going to go into details, it doesn't really matter. This transition is an optical transition. It oscillates at hundreds of terahertz, okay? But the line width of this transition is 1 millihertz, okay? So that is kind of remarkable. It means that there's something called the quality factor, where you compare the line width of something of a resonator to its frequency, okay? And what it means is if you start the thing sort of resonating, how many oscillations will it resonate for? So for example, with a pendulum or a simple harmonic oscillator, if you start it ringing, how long will it ring down? How many oscillations, how many swings of the pendulum will it undergo before it dies out? Okay, this thing will swing 10 to the 18 times before it dies out, okay, on this transition, which is kind of insane. Okay, that's a huge number. And that's really what we're taking advantage of to make a very, very good clock, okay? But it turns out that there's a cost to be paid, a price to be paid for using optical transitions, which is that you're probably all familiar with the concept of the Doppler shift, the idea that when something moves with respect to you, or when you're moving with respect to radiation, the radiation frequency gets shifted, right? So that's true for sound waves. When we hear an ambulance coming towards us versus moving away from us, the frequency of the siren changes. And it's also true for light. So as you're moving towards light or away from light, the frequency of the light and therefore the color of the light changes. And so what that means is we're trying to take advantage of this incredibly narrow line with the transition. But our atoms are moving because they're at a finite temperature, and that shifts the frequency of this transition and effectively broadens it out, okay? And so to take advantage of this transition, we need to have very good control over the motional state of these atoms, and we need them to be very cold. So we use a technique called laser cooling, okay, that I'm not going to explain, although if you want to ask about it, you're welcome to cool these atoms down from an initial temperature of 800 Kelvin, which is quite hot. They come out of an oven from a solid chunk of strontium at 800 Kelvin, and then we laser cool them with a bunch of lasers down to 2 millikelvin, so just a thousandth of a degree, a couple thousandths of a degree above absolute zero. And this is a picture of that. So that glowing white or blue, it's actually blue, but it's sort of saturating the camera. That glowing blue ball there is a cloud of a few hundred million strontium atoms. at a temperature of just a few, a couple thousandths of a degree above absolute zero, sort of levitating in space using a combination of lasers and magnetic fields. Okay, and I took that with my cell phone camera. There's no tricks or anything here. This is really what it looks like. It's really beautiful to see. You can just see it by your eye, with your eye, right? But it turns out that's not cold enough. So we do a second stage of laser cooling and cool them down to 2 microkelvin, okay? So this is now 2 millionths of a degree above absolute zero or so. Now, just so you know, atoms at room temperature in the air are typically moving at the speed of sound, okay, to give you some sense of how fast they're moving. These atoms, once they're down at 2 microkelvin, are moving at the speed of a snail or so, okay. Very slow. Still, it turns out that's actually not cold enough. So by the way, this, in case you're curious, this is what it's sort of how we can tell how hot they are. You let them go, and then you watch how the cloud of atoms expands, and then you use that to measure. So this is an example where we measured 4 microkelvin. Now we've actually, these were some of the first measurements we did like this, but now, we typically cool them down to even below a microkelvin. But okay, and this is a standard technique in atomic physics. Not something my group invented or anything like that. But, okay, but it's just cool to sort of see and watch this cloud of atoms kind of expand as it falls, and it's falling because of gravity, by the way. But anyway, so okay, so 2 microkelvin is actually still too hot. Okay, even though they're 2 millionths of a degree of absolute zero, even though when we do these experiments, this is probably one of the coldest places in the universe. It's still, these atoms are still too hot, because if you look at the Doppler broadening from that finite temperature, it's still 40 kilohertz, and we're trying to take advantage of a 1 millihertz line width transition. So you need an extra ingredient, and basically what we do is we hold the atoms tightly in place, okay? And we do that using light. So we trap them in what's called an optical lattice, which is a standing wave formed by 2 counterpropagating laser beams, okay? And it turns out that these atoms, if you pick the right frequency of light, these atoms want to sit at either, depending on the frequency of the light and the internal transitions of the atoms, they either want to sit at the field maximum or the field minimum, okay? And we pick a specific frequency for the atoms we work with where they want to sit at a field maximum. So if you take a laser beam and you focus it down, and then you reflect it and focus it down again so that it interferes with itself, you get a standing wave of light that looks kind of like a stack of pancakes, and the atoms are like the blueberries in the pancakes, okay? Or the chocolate chips, if you prefer chocolate chips, okay? And what this does is, if you confine these atoms strongly enough, their temperature doesn't really matter anymore for these transitions, okay? There's different ways to think about it, but it's really a quantum mechanical effect that now they can only have certain energies, again, because of quantum mechanics, if they're very tightly confined. And so you can see that if we don't trap the atoms, which is the top plot, you get this broad line that's about 40 kilohertz or so. And then we start to turn on this trap, and you get these very weird line shapes. There's actually some very interesting physics going on here that looks a lot like electrons moving around inside of solids. And so one of the projects I worked on as a postdoc, which this figure is from a paper that I wrote as a postdoc, was actually studying that kind of solid state, kind of condensed matter-like phenomena using these atoms as a kind of quantum simulator. But that's a whole other thing. You keep turning on the lattice, and then you get to the point where you have this very narrow transition, and then these side bands, where the side bands actually correspond to the atoms sort of changing their motional states and to their finite temperature now. And you've now isolated this clock transition, the internal transition of these atoms from this motion kind of completely. Okay, so now we have our new our atoms that we're going to use. We have this new counter that's no longer counter, but now the question is, what's your local oscillator going to be? It can't be one of these little quartz tuning forks anymore, because they don't oscillate at high enough frequencies. Actually, now your local oscillator is actually a laser. Okay, a laser is a kind of a clock that ticks at an optical frequency, although we don't normally think about it that way. And so what we're going to do is we're going to shine this laser on our atoms and see if it's on resonance, and then we can count the frequency of that laser with one of these laser frequency combs. And that's how an optical atomic clock works. So since the invention of optical atomic clocks, these clocks have gotten even better. They're actually improving at an even faster rate than the microwave clocks were before. They're now improving by about a factor of 10 every 3 years or so. And they're now accurate to 1 second in 14 billion years, or even better than that. So what that means is, now if you had these 2 clocks ticking from the age of the universe, from the Big Bang, all the way to now, they would agree on the age of the universe to better than 1 second, right? And it's just hard to even, I think, wrap your head around like the numbers on this scale. but I'll try to give you some more sense as we go along of just how remarkable this is. Okay, so this has opened the door now to a whole new set of applications. I showed you the applications of these microwave clocks. Now there's exciting new applications of these optical clocks, a lot of which have to do with kind of fundamental physics. And this is really my primary area of interest and area of research, is exploring and developing these kind of new and emerging applications of these optical clocks to fundamental physics. And so the rest of this talk, I'm going to tell you about one specific example, which is about sort of testing relativity. And in particular, I'm going to tell you about one specific aspect of relativity, which is this thing called either the gravitational redshift or gravitational time dilation. Okay. And the idea is that gravity actually sort of changes the rate that time ticks at. Okay. And so if you're on the surface of the Earth, we're of course experiencing Earth's gravitational field. And if you raise a clock up in Earth's gravity, then it will tick faster than an otherwise identical clock that's just lower in Earth's gravity. Okay, like nothing else different, just the effect of gravity and relativity will change the frequency that the clock ticks at. And what this actually corresponds to is not any kind of error in the clocks. This is really that like physics happens at a different rate up here relative to here, right? All the physics is the same up here, so it's not that anything really changed, but that's the thing about relativity. Everything is relative, right? And so physics will just happen faster here than it will lower down. Those of you who saw the Christopher Nolan movie Interstellar might know that this was like a big plot point in Interstellar, where they went close to a black hole. They went down on this kind of weird water planet thing, and when they came back, the person who didn't go down had aged like 20 years and they'd only been down there for an hour, right? And that's an extreme version of that because they're very close to a gravity, to a black hole. And so they're experiencing, a large amount of gravity, and they're also changing the height by a fair bit because they went from a spaceship down onto the surface of the planet that was very close to this black hole. Okay, but actually this is a real effect that happens on Earth too. And there was a beautiful experiment in 2010 where they used two of these optical clocks and they raised one clock a foot with respect to the other one. And you can see the subtle change in the frequency of the one clock with respect to the other at a part in about, 4 parts in 10 to the minus 17 here for a foot height difference, okay? Just to give you a sense of scale, 1 meter will give you about 1 times 10 to the minus 16 change in the passage of time on the surface of the Earth, okay? And so what this actually means is that your head is slightly older than your feet. You can go through the math, and I think it works out over if you assume that you spend half your time upright throughout the course of your life, and if you live to the ripe old age of 100, it's something like 40 microseconds that your head is older than your feet, when you die, okay? But so that's a very small effect, but it's also a real effect. It's a measurable effect, right? And we can measure it with these clocks now. And you can see that as these clocks have gotten better, again, we're getting more and more sensitive to this effect, to the point where actually now with this 1 times 10 to the minus 18, that's the redshift at a centimeter. And this is actually becoming a problem because we would really like to be able to compare. These clocks are hard to make, okay? And so typically in these standards institutes, like each standard institute has 1 or 2 of these clocks. And they're all different, and you want to compare them to each other. And there's lots of other interesting physics that you can learn about if you do compare different atomic clocks to each other. But actually now, to compare them at their level of performance, you need to know the height of these clocks with respect to Earth's gravity at the centimeter level. And we actually don't have a way of measuring the heights to that level of precision across kilometer scales. So basically we're entering this, what's called the geodetic limit, this limit where if I wanted to compare clocks that I have here in Berkeley to, the lab where I worked at Boulder, in Boulder, Colorado, we can send light back and forth there, but we actually don't know their heights with respect to Earth's gravitational potential well enough for those measurements to be particularly meaningful in terms of learning about how good the clocks are or what their frequency ratios are, things like that, okay? And so that's actually a big problem for these clocks, but you can also turn it on its head and say, if you think you know those frequency ratios, or if you build 2 identical clocks and you trust that you can keep them ticking at the right rates, now this is a way to measure Earth's gravity and to measure those heights better than we can otherwise do it. And that's something called relativistic geodesy. And this is something people are just starting to do with these clocks. So they're just starting to build versions of these clocks. And I will say, I'll make a pitch, by the way, that Andrew Ludlow is one of the people who's who's at NIST and who's pushing these clocks, does very related research to what I do, but is particularly interested in doing this relativistic geodesy. He's trying to make this is from a paper, from his paper, and he's trying to make portable versions of these clocks to take them around and make measurements of this. And he'll be speaking next Wednesday. He'll be giving the AMO seminar in this department. But anyway, so okay, so but people are starting to do these, but they're just starting to reach the level, and actually we can't make portable clocks that we can take out into the real world that are good enough yet to outperform kind of other ways of doing this geodesy, but it's just starting to get there. And so this is a really interesting emerging application. Another interesting thing that I won't really go into detail about, but that motivates some of my research, is to think about how these kind of relativistic effects interact with the fact that these are quantum systems, that these atoms we can control their states very well. They're really described by quantum mechanics, and we can do things. And in fact, this is research that other people in this department, like Holger Mueller, do, like take atoms and split them apart and take one atom and put it in a superposition of being in two different places at the same time. And now you can start to ask questions about, well, like, what does that mean if an atom is experiencing two different times while it's in two different places, And those are the kinds of experiments that we can start to explore with these clocks, which I think is very exciting. And so you can kind of say, well, like, we're entering this interesting regime. This is really where I want to play around. So, and also this is where we want to now this is a regime where we're starting to outperform other ways of measuring, Earth's gravity. This is a regime where we can start to do tests of relativity in the lab. Let's build a clock to do it. And so that's what we did. So we built this strontium optical lattice clock for fundamental physics. Okay, we worked very hard to do this. These are atoms trapped in this optical lattice that I told you about in our experiment. This is our clock that we're going to use to compare them. This is our laser. Okay, and we set everything up. We get it to work, and we actually get pretty good performance. Okay, I'm not going to go into technical details, but this is sort of showing you what it looks like when we kind of probe these atoms with this laser. We get these fringes, and then over time, these fringes start to die down. And that tells you about how long you can compare the atoms to the laser. And as I told you before, when I showed you this equation, the longer you can kind of compare the atoms to the local oscillator, the better the performance of the clock, right? And so, okay, so we built this thing, we do it. And then the last thing you need to know about is that the way clocks typically work, the longer you measure time for, the better sense of how much time has passed you get, which makes sense, right? So like if I count a couple of seconds, okay, I learned something about the passage, but if I count 1,000,000 seconds, I can much more precisely tell exactly whether, 1,000,000 or 1,000,001 seconds have happened, right? And so that's what that means is that the performance of the clock gets better the longer I run it for. And you can see this. So this is a clock comparison, and basically how fast this averages down tells us how fast do we learn about time, and how sensitive do we get to these effects like relativity and stuff. And so this is the actual performance of our clock that we measured. This is quite good. So it tells you we can measure a frequency difference of 6 times 10 to the minus 15 at 1 second. Okay, and then it averages down the square root of the number of times. So then if we want to do 10 times better, we have to measure for 100 seconds. And if we want to do 10 times better than that, you have to measure for 100 times longer than that. Okay, et cetera. Okay, and so then you can say, well, it sounds great. Let's go measure the effects of relativity in the lab. Let's try to measure it at a millimeter, which is kind of, really state of the art, because that's what we want to. We want to do better than this relativistic geodesy. We want to measure at these kind of small scales. And then it gets kind of depressing. So you just plug in the numbers, and it's 114 years of averaging with this clock, right? And that is just to make one measurement, like one measurement at this level. And actually, most of what we spend our time doing is not making measurements like that. It's actually trying to understand all the other things that could be screwing up that measurement, which is called evaluating systematics, or doing sort of, a systematics evaluation. And so this sounds really bad, because this is like a no-go. You can't measure an effect of this, and I can't convince my grad students to take 114 years, to finish their PhDs, right? But the good news is, of course, we saw this coming. This is not a surprise to us. We knew this, and so we came up with a way around it, okay? And that's inspired by other experiments where you have similar issues, where basically what's actually limiting the performance of this clock is not the atoms, but the laser that we're using to probe them. Okay, and similarly, like when you make LIGO, LIGO is trying to measure very, very small changes in length using a laser. But the laser frequency is bouncing around. And so if you just tried to measure those changes in length, just kind of using standard laser ranging or whatever, you wouldn't be nearly good enough. But if you make an interferometer that has two arms that are the same length, then actually the laser noise cancels out because it's the same in both arms of the interferometer, and you can measure differential changes in those arm lengths much, much more precisely. And we're going to do exactly the same thing in our clock. So rather than having one clock, we're going to have two clocks or more, as you'll see. And we're going to shine the same laser on both of them and hope that the noise on the laser cancels out, and it lets us measure frequency differences between these clocks much more precisely. Okay, so this is how we actually do that. Okay, this is showing actual camera images from our experiment. So those the red blobs there are the atoms. And what we did is we loaded one set of atoms into our lattice, and then we turned the lattice from a standing wave into a running wave. You can think about it like one of those moving walkways at the airport. We transport the atoms over, and then we load another group of atoms into another part of the lattice, and we transport them all back so that in the end, they're kind of symmetric with respect to the focus of this laser beam. Okay, so when we're done, we have two clocks now. You can see I turned it this way because of the aspect ratio of the slide. So gravity is pointing down, right? So this is actually vertical. Okay, and so now we can do something crazy. We can interrogate one of these clouds of atoms for way longer than our laser will allow us to. And that just gives us random noise. Okay, you take my word for it. There's no information in the data that I've plotted here. It's just completely random, shot to shot, what the outcome of the same. I'm doing the same exact experiment over and over again, and I'm just getting noise. Okay, but now we have two clouds, and we're comparing them to this laser at the same time, and so you get two sets of random noise. But if you look at them, you can see that they're actually kind of correlated. Like there's some regions where they're both high, and there's some regions where there's both low, but it's kind of hard to make out from plotting things this way. So I'm going to plot this differently. Okay, what I'm going to do is I'm going to plot the outcome for one region on the x-axis and the outcome for the other region on the y-axis. So each of these experiments now is a point on a two-dimensional plot instead of, okay. And then I'm going to plot all the same data that I'm showing you now one by one. Okay, and what you can see is that indeed they're extremely highly correlated. Okay, what this actually corresponds to is sampling two offset sine waves and randomly sampling points on those two sine waves. So I cannot predict where on the sine wave I'm going to measure. Each measurement is completely random, but because I'm sampling two sine waves, it ends up giving me an ellipse. Okay, and I will always get an ellipse if I have two sine waves, regardless of what the offset is. I mean, I'll show you in a second that you can get different kind of shapes of ellipse, but okay. And now I can fit to this and learn about the frequency difference between these clocks without being limited at all by what my laser was doing. Okay, just to show you, if you had two sine waves that had no offset, you get a line, and we can engineer that situation. If you have two sine waves that are completely 180 degrees out of phase, you also get a line pointing the other way. And if you have two sine waves that are 90 degrees out of phase from each other, you get a circle. And and everywhere in between, you get some kind of ellipse, and we can just use that to figure out exactly what the frequency difference of these clocks is. And what that allows us to do is to go from this limit of interrogating for only 100 milliseconds that we had when we just compared the laser to a single cloud of atoms to 26 seconds. And now we've even pushed that out to like 70 seconds. Okay. And that gives us really good performance for these clocks. Okay, so we can measure the frequency difference between these two clocks now with a stability of about 7 times 10 to the minus 18 per square root hertz. Okay, to compare that to the number I showed you before, it's about 3 orders of magnitude better. And remember that things to average down, it's with that amount of time squared. So this is about 1,000,000 times shorter averaging to get to the same level of stability. And so it would take us 114 years. I told you to average down to 10 to the minus 19 before. Now it only takes 1.5 hours to average down. And that's a measurement I can convince my grad students to do, right? And that's also a measurement where I can measure systematics and things and still get a reasonable answer. We don't have to stop at just 2 clocks though. So we can load as many regions of this lattice as we want. And so this is showing an animation where we load 6 of them, okay? And that's also kind of powerful because now we can do comparisons between all these clocks at the same time. So here I'm showing you 5. That in that movie we loaded 6, but we did this experiment with 5. Okay, so you have 5 of them, and you learn about the frequency comparisons between all of these clocks simultaneously. So you get 5 choose 2 comparisons simultaneously, or 10 different ellipses all as you take the data, okay? And this is what we're going to use to do a test of relativity. So as I told you, we expect that these clocks will tick faster if they're higher up. And we have this vertical array of these 5 clocks that are evenly spaced with 2.5 millimeters of spacing between them, so that the total spacing from this one to this one is 1 centimeter. And so when we do these comparisons, this ellipse is basically telling us about the frequency difference between a clock here and a clock at 1 centimeter higher up. But we're also learning about 4 frequency comparisons between clocks that are separated by 2.5 millimeters. Okay, and so you can see that actually with the performance that we get at 2.5 millimeters, we should only have to average for 30 minutes to be able to see the gravitational redshift between these clocks. And you would say, great, you can just take an afternoon and you're done, right? But of course, that's not true. As I mentioned, you have to characterize all of the other stuff that could give you frequency shifts between these clocks. A nice feature of these kind of measurements is that all these atoms are basically in the same environment to lowest order. So things that normally limit these clocks, like exactly what's the magnetic field of the environment, exactly what's the electric field, exactly what's the temperature, we don't really care as long as it's the same between all of these clouds of atoms. But if there's any difference between the magnetic field between these clouds of atoms or between the electric field between these clouds of atoms, then you care. And so we had to characterize all of these differential frequency shifts that correspond to basically, gradients in our apparatus. And I'll give you one very quick example. I know I'm running out of time, which is what's called the differential black body radiation. That's what BBR stands for, shift, okay? And this is actually, to me, a somewhat surprising effect, which basically says that because the surrounding environment is not at 0 temperature, because it's at a finite temperature, the walls and windows of the vacuum chamber that these atoms are inside of emits black body radiation. And that's an electric field, and it shifts the frequencies of my atoms. So my atoms actually care about the surrounding temperature that they see in the surrounding thermal environment, okay? And that would be fine if the atoms all saw the same environment, but one cloud of atoms is higher than the other cloud, okay? And so if the top of the chamber has a different temperature than the bottom of the chamber, one's closer to the top and one's closer to the bottom, and that's going to look like a gravitational redshift. It's going to look like one clock, shift the frequency of one clock with respect to the other. And so we characterized this. We looked at how these frequencies of these pairs of 10 pairs of clocks shifted by intentionally making one side of the chamber hotter than the other. We literally just heated it up with a heater, okay? And we also have thermometers that we glued to these windows. We put sensors here and here, and we measure this, and we looked at how these frequency shifts behaved. And you can see that we get this linear shift that looks just like a redshift would, and it has a slope of 4 times 10 to the minus 18 per centimeter per Kelvin. Okay, whereas the redshift is 1 times 10 to the minus 18 per centimeter. So what this means is if you have a quarter of a degree Celsius difference between the top of the chamber and the bottom of the chamber, it'll look like a redshift, or the effect will be as large as the redshift. And so you have to measure the temperatures of the top and bottom of the chamber very well and account for this effect, which is what we did. We had to do that for all of these different systematics. This is most of our time. This was basically a year of work to do all these things. And then the last thing is, we don't want to bias ourselves. Like, okay, my prediction would be that Einstein is correct, and that we're going to measure the redshift that we expect, and that are, and of course, there's been a lot of other tests of relativity, including measurements of these redshifts at much larger scales. So it would be very weird and surprising if we got a different answer. But we don't want to bias ourselves towards getting the answer that we expect. For this to be a real test of relativity, you want to make sure that you're not tricking yourself. And you can see how many different things that we had to account for. It's very easy to convince yourself, oh, maybe I should slightly adjust this because of that. And, and so what we did is we did all of these measurements blind. So our analysis software for taking this data and analyzing the data added an offset that looked like an arbitrary redshift. So that as we were taking the data, this is the value that we measured. You can see that all the data points kind of lie around this line pretty nicely. And the actual redshift that we expect is this black line down here. So we're even measuring a redshift with the wrong sign, but that's okay because we knew we were applying some arbitrary offset. We just didn't know what it was, okay? And this green region is showing you the range of possible values of the offset. So we knew we weren't screwing up too badly, and that it was at least possible to be right, but we didn't know if what we were measuring the right thing or not. And once we were done and we'd settled on everything, how we were going to account for all of these systematic effects, once we were done taking data, that only then did we remove this blind and find out if we'd measured what we expected or not. And I have to say that I was incredibly nervous when he did this, but just to give you that same feeling, a little bit of the same feeling, I'm going to show you what that looks like. Okay, so now I'm going to remove the blind, and you can see that our data agrees very nicely with the expectation. Okay, and if we zoom in on this, you can see that actually the statistical average of the data that we measured, which is this red region, doesn't agree. But then the blue region accounts for our systematic uncertainty, basically how well we measured things like this thermal gradient, how well we have it characterized, magnetic field gradient, everything like that. And within our uncertainty about our systematics, it agrees very nicely with the expected value for the gravitational redshift. So, and here's our systematics table. So this is showing you our uncertainty for all of those different effects, how much those actually shift the frequencies, and then how much uncertainty we have in it. Okay, and we get this nice agreement. But I'll show you my favorite plot of this whole thing. This is showing you how the frequency difference is changing between these clocks as a function of height. Okay, and so you can actually see the gravitational redshift across 1 centimeter. And just to give you a sense of scale, this is showing you a penny at the same scale, right? Rotated. But so we're really now able to measure the redshift between the height of a penny, or the thickness of a penny, which I think is pretty remarkable. And that bodes very well for using some of these same techniques to take these clocks out into the field and to try to measure Earth's gravity and do this relativistic geodesy between clocks over much larger separations. Okay, we can also view this as a test of relativity and say, what if the redshift doesn't, or this gravitational time dilation doesn't behave the way that we expect? And we can kind of parameterize how much of a limit we can put on modifications to relativity. And we can plot it here. And you can see that we're not setting nearly as stringent a bound as of a lot of other measurements, but we're doing it in a totally different length scale. So most of these other good measurements are measuring at many meters, or even millions of meters in the case of these Galileo satellite tests and gravity probe A. These are space-based tests. We're sitting up here near some of the earliest tests of relativity that were done at this kind of 20-meter scale, but now we're measuring in this kind of new regime of centimeter scale. And one point I'll make is the very first confirmation of this gravitational time dilation, this redshift, was by Pound and Repka in 1960. And 5 years later, they improved their bound by about an order of magnitude or so. And I think something like that is very realistic for us as well. This was just our first attempt, so I think we can do that. And then I'm planning here at Berkeley to build kind of a meter scale experiment. And if you plug in the numbers for that level of systematic accuracy and everything for a meter scale experiment, now in the lab you're competing with space-based tests of relativity, which I think is cool. And you're also measuring things on a scale where we can put these atoms in superposition and things like that and start to see how quantum mechanics sort of interacts with relativity. So I'll just kind of end by showing you this other list of lots of other things that we want to do with the same apparatus. We have a long list of experiments that we want to do with this. Test of relativity is just one example, but we also can use these to search for new particles and new forces, to try to look for certain candidates of dark matter as a test bed to test and sort of verify levels of performance for future gravitational wave detectors using these clocks, and those kind of things. And so with that, I'm just going to acknowledge my group. So these were my group before I moved from Madison, and some of these people, wanted to stay in Madison for various reasons. Some people graduated, things like that. So the group has shrunk a fair bit. And I want to just especially acknowledge the people who did the work I just told you about. And in particular, Xin Zhang and Jack Doldy are both moving with me from Wisconsin to Berkeley. They're going to be the ones that are going to help me move this experiment and get it going again here. And I'm looking for grad students and undergraduate researchers and things to work with me on this experiment here. And I will stop there and thank you for your attention and take questions.
Thank you. That was a preview of the colloquium. I look very much forward to attending the colloquium as well. Very nice talk. Are there any questions?
do you use laser to cool down the atoms?
Okay, that's a great question. Light has momentum. That's like not an obvious statement, but it is true. So every time an atom absorbs a photon, it gets the momentum kick. And so if an atom is moving towards a laser beam and then it's absorbing photons from that laser beam, it's getting pushed in the other direction. Okay. And then the trick is what you do is you tune your laser beams so that they're what's called red detuned or lower in frequency than the transition of the atoms, so that if the atom was stationary, it wouldn't absorb the light. But because it's moving, if it's moving towards the laser beam, it gets a Doppler shift. The light is Doppler shifted and it absorbs more of the light. And so then you shine laser beams like this from all the directions. And now the atom always gets more kicks from the lasers pointing in the direction opposite that it's moving. And so it always gets slowed down no matter which direction it's moving. And that's called laser cooling or Doppler cooling. And that works extremely well and allows you to cool these atoms down to these kind of preposterously low temperatures. There's more to it than that. I'm skipping over a lot of things, but that's the basic idea.
So that's pretty much the same as you keeping an atom at a specific place.
So actually, that does not hold it in a specific place. It actually just makes it want to move more slowly. So this is actually something called, what I described to you is something called optical molasses. And you can imagine it as like something moving around in molasses. It just slows it down. It's a lot of drag, if you want to think about it that way. But to hold it in place, you actually need an additional ingredient, which is you use magnetic field gradients and you change the polarization of the light. And so the combination of those two things applies a restoring force and actually makes a conservative potential. And that's how you do this. So you combine shining lasers from all 6 directions on the atoms with a magnetic field gradient, and then the atoms want to sit at the magnetic field 0. So they're sitting in the middle of this kind of combination of light and magnetic field trap, and they're actually suspended, you know, and sitting there fairly happily, and they're constantly scattering the light from the laser beams, which is why they're glowing. That's why you can see them. If you turn the lasers off, they will fall out of the trap.
Are you trying to make like a bunch of clocks for like that's like a meter tall?
That's the idea. We're still in the design phase, so I'm not sure that we'll be able to have the capability to make a sort of a linear array the whole meter high. We might just have a few regions where we have atoms, and in between, it depends, because putting viewports on there and things makes the design, you know, complicates the design, and it's places where you can have vacuum leaks and reduces the vacuum and everything. So we probably won't literally have an array of clocks a meter high, but we'll have like a few clocks down here, and then maybe halfway up another set of array of clocks, and then a meter, you know, and then another half a meter up another one, something like that. But we're still in the design process.
I couldn't exactly tell from the scale of but what exactly is the scale of each atomic clock?
Right, that's a good question. So just to go back, I can also just answer it in words, but we can look at a picture while I do it. So you can see that this is 2.5 millimeters. The actual spatial extent of a single cloud is in the like hundreds of microns-ish size scale. It sort of depends a little bit on so that's set by basically the magneto-optical trap that we load the lattice from. But it's like, I think the vertical extent is something like 200 microns or so. Yeah.
How do you use atomic clocks for dark matter detection?
Okay, great question. So there are it's only for certain dark matter candidates. It's not for heavy ones and ones that behave more like particles. So it's not for WIMPs. But there are these ultralight dark matter candidates, things like axions, where the dark matter is more like a background field. And if you make certain assumptions about how that dark matter couples to matter, as these atoms move through that field, the frequencies of the transitions get shifted because the dark matter is interacting with either the atomic nucleus or the electrons of the atoms. And so the way this gets talked about is it's like the fine structure constant is varying, and that's shifting the atomic frequencies. And so basically, if you compare the frequencies of two different atoms that have different dependencies on the fine structure constant, you can see whether or not we're moving through this background field. Or you can compare two different clocks that are in two different places. And if the field is varying, then you can see it that way with two identical clocks. So the idea, to show you kind of in this cartoony form here, you can kind of imagine like we're moving through, say, a clump of dark matter, and we're comparing these two clocks that are at two different points, and you get kind of a shift as first one clock and then the other clock moves into that clump or moves out of that clump or things like that. That's the idea. I mean, it's only for certain candidates. It's only under certain assumptions, but if you look at the numbers, these kinds of measurements that we can do with our experiment could cut into some phase space for some candidates people think are interesting. You know.
Is it useful to go to higher frequencies than optical?
Great question. Yes, definitely. People are trying very hard to make sort of UV clocks. It turns out that what people think are, there's a couple different ways to do that. But what people are very excited about these nuclear transitions. So basically the transitions of a nucleus, not of electrons around the nucleus. And there is a thorium has a nuclear transition that's kind of in the UV part of the spectrum. And what's really nice about that is that those transitions are even less sensitive to things like magnetic fields and electric fields and the temperature and stuff. So if you could make a clock like that, it would be much better than these clocks, and it would tick at a faster rate. There's challenges because now you need to count the frequencies of UV, you know, and that's hard, but people can barely make these kind of frequency combs at UV that would allow you to do that. But the real challenge is that no one's been able to actually really find that transition directly. So there's like sort of indirect measurements of it. And recently, for the first time, people said that they saw that they could excite, that they were able to excite that transition, but they're still not able to really like measure it the way that you need to make a clock. So that's still, there's a lot of work on that, including like my postdoc advisor is trying to, is working on that, and many other, you know, groups around the world are trying to find that transition. But it's yes. So the short answer is yes. You know, if you can keep moving higher in frequency, you'll keep making a better clock.
You mentioned because of quantum case of gravity, what you have in mind?
Well, okay, so the basic idea is kind of along the lines of what I alluded to, which is suppose that you have an atom that you're using as a clock like this, and you also put it, let me pull up this thing, and you also put it in a superposition. So there's these proposals like this that basically say you take an atom and you put it in an internal superposition of being in two states, and then you also put it in an external position of being in two different places at the same time. And then basically because of the gravitational redshift, if those two different paths are at different potentials, then when you recombine your atom, when you do an atom interferometry experiment and you interfere the atom with itself, at certain points, it basically has which path information because of the redshift. And you would actually see that you'd stop to see interference fringes in your interferometer. And that's a prediction of kind of like the most naive way that we would combine relativity and quantum mechanics. It's probably right, but we don't know. Nobody's been able to do that experiment. So those are the kind of experiments that we'd like to do to kind of see like, okay, when you write T down for a quantum mechanical system for the evolution of a Hamiltonian, you know, is that T proper time? Is kind of one way to frame the whole, you know, thing. And the answer is almost certainly yes, but you know, that's not something that we've seen directly.
What are the in your graph which has
The ellipse?
Yeah.
Yeah, okay. So it's the outcome of the experiment for one region versus the outcome of the experiment for the other region. Okay, so so what the experiment is that measurement is excitation fraction, but what that really means, let's see here. What that really means is how many atoms were in the upper state versus the lower state. And I guess this is probably the last question.
Yeah. I think we need to
wrap it up.
Yep. I have more questions.
We can talk about it offline, but yeah, so it's plotting basically the outcome of one region versus the outcome of the exact same experiment for the other region.
All right. So since we have to wrap it up here, let's thank our speaker one more time. Just as a reminder, we have sign-in forms at the front if you did get a chance to sign in. You can also fill out that form again. There's a section where you can type a question that we can relate to Shimon if you're not able to ask it right now. But yeah, thank you for coming.